Okay, so it's 4 o'clock, so I think we should get started. We already have 45 people, so it's a good turnout. So welcome to our last talk for this season. So our plan is that in the next quarter, in the fall, we'll have in-person colloquium. So this will be our last Zoom colloquium for now. The speaker is our own David Simmons-Duffin. So he has been a faculty member at Caltech since 2017, and he was promoted to an associate professor last year. So before coming to Caltech, he received his PhD from Harvard with Lisa Landau as his advisor and was a long-term member of the Institute for Advanced Study. He's an expert of the bootstrap approach to conformal field theory, which he will tell you about today. His work has been recognized by many honors and awards, including DOE RE Career Awards, Sloan Research Fellowship, and Herman Weyl Prize, among others. He's a principal investigator of the Simons collaboration of the non-perturbative bootstrap, and he hosted its annual conference and summer school at Caltech in 2018, which gathers about 100 people, I guess, working on this approach. So he said he's happy to take questions during the talk, though if it is going to be a long conversation, it should be deferred to the Q&A session at the end. The title of his talk is Carving Out Theory Space. Okay, so David, please start.
Okay, thanks a lot, Hiroshi, for the nice introduction. And it's nice to be here giving this talk. This is the first time in a while that I've had to dress up on my top half, so I hope it's well. Okay, so this talk will have 2 parts, and each part has a motivating physics problem. Hold on a second, I'm having some Zoom difficulties for the moment. Okay, so the first part is about the conformal bootstrap, and the second part is about gravitational effective field theories. And these 2 parts are connected by both the conceptual and practical reasons that will hopefully become clear in the course of the talk. So every year, Caltech undergraduates in physics 2C and 12C get to see a really awesome demonstration of the superfluid transition in liquid helium. And the demonstration starts with a bunch of liquid helium in a glass container so you can see what's going on. And the demonstrator pumps on the helium to lower its temperature. And as the pumping proceeds, the helium boils, and it boils more and more frantically, bubbles and bubbles and bubbles and bubbles and bubbles, until all of a sudden, in an instant, it stops. And what's happened is that we've reached the superfluid transition. And the mixture of superfluid and normal helium has an incredibly high heat conductance, so high that it's able to equilibrate temperatures across the sample incredibly quickly, enough that it stops the boiling. And if you look at the plots that so this whole time during the demonstration, there are measurements being made on the helium, and if you look at the plots of the plot of the heat capacity, you'll see something really interesting happen, which is a spike in heat capacity as a function of temperature. So this is a plot of the heat capacity as a function of temperature in liquid helium, and the spike occurs just above 2 degrees Kelvin. It's the so-called lambda point transition. And this spike is characteristic of a special kind of phase transition called the second order phase transition. The physics of a second order phase transition is really spectacular. It involves a kind of fractal structure of density perturbations at all distance scales. So you can think of it as like you have your liquid helium, and it develops some bubble of superfluid, and inside the bubble of superfluid is a bubble of normal fluid, and inside that is a bubble of superfluid and a bubble of normal fluid, and bubbles and bubbles and bubbles and bubbles and bubbles. And as you get closer and closer to the critical temperature, Tc, this structure of the structure of nested bubbles goes all the way from macroscopic scales down to close to molecular scales. This crazy fractal structure is described by strongly coupled conformal field theory, in this case, the critical O2 model. And this conformal field theory makes a prediction for the shape of this heat capacity curve as a function of temperature. It predicts that the curve should be a power law in T minus TC. And this power here called minus alpha, this power is called the critical exponent. And this critical exponent is determined by some observables of the conformal field theory called scaling dimensions, here delta S and delta sigma. Okay, the superfluid transition in liquid helium, one of the reasons it's interesting is that it is the one of the cleanest critical systems for experiment. And the most precise measurements done on this system, in fact, the most precise measurements we have of any critical system were performed in what's called the lambda point experiment on the space shuttle Columbia in the early 90s. And the reason for performing the experiment on the space shuttle is that in microgravity, there is no pressure gradient. If you do the experiment on Earth, there's a pressure gradient throughout the sample, and the critical temperature depends a little bit on the pressure. And this means that if you have a pressure gradient, you can't tune the whole sample to the critical temperature at the same time. Instead, you'll just end up tuning some two-dimensional slice of the sample to the critical temperature. And this makes it hard to gather statistics. If you instead do the experiment in microgravity, then there's no pressure gradient and the entire sample has the same critical temperature. You can tune the whole thing close to the critical temperature and get much better statistics and make a much more precise measurement. This measurement was done in the early 90s, and they obtained a value for this critical exponent alpha, which determines the shape of this heat capacity curve at the transition. Unfortunately, this measured value of alpha was in discrepancy with Monte Carlo simulations of this transition. So there was an 8 sigma discrepancy with the best Monte Carlo results that persisted for a few decades. So this is an example of a strongly coupled conformal field theory. I'll explain a little bit more about what that means, that has relevance for the real world. And you might think that we should attack this with field theoretic techniques. But the problem is that this theory is strongly coupled and it resists traditional calculational techniques. We need a different approach. And there is indeed an approach that works for this system called the bootstrap. The idea of the bootstrap is to use physical consistency conditions to constrain observables. So it's sort of like a souped up version of doing your entire physics problem set using dimensional analysis. And it's not obvious whether it's actually a good idea. I mean, we can write down physical consistency conditions, but how powerful can these conditions actually be? And the 3 key principles that will play an important role in this talk are unitarity, symmetry, and causality. And I'll talk about a little bit about what each of those are. And one of the surprising lessons from the last half century of the bootstrap is that these principles interact with each other in surprising and powerful ways. And they have implications that go beyond what one might naively expect. And in fact, in some cases, allow one to do precise computations. We don't yet know the full implications of these principles or other physical principles that we might find. This is an open area of research that we're actively working on. And every once in a while, there's a surprise. There's a new kind of physical system that can be attacked with these techniques that we didn't realize before. Okay, so let me talk a little bit about these constraints in the context of the theory that describes this superfluid transition in helium. So I said that the transition is described by a conformal field theory. So let me explain what conformal symmetry is. A conformal transformation is a transformation that locally looks like a rescaling and a rotation near each point. This is my favorite picture of a conformal transformation. It's a drawing due to Escher. And you can see that this drawing is warped in some kind of strange, funny way. But the nice thing about it, the thing that makes the picture kind of work, is that the warping is angle preserving. So if you zoom in near each point, the angles are the same as they would be in a normal picture. And that's because near each point, the transformation that's happened is just a rescaling and a rotation. And this is the defining property of a conformal transformation. If you have a field theory with conformal symmetry, that symmetry is very powerful in constraining and organizing the theory. And one of the first implications is that you can organize the states of the theory using the symmetry. So in particular, you can categorize the states according to their quantum numbers under the generators of the conformal group, just as we would categorize states according to their quantum numbers under translation. So that's the quantum number under translation is momentum. We can write down the momentum of a state. And similarly here, we have other symmetries that let us write down other quantum numbers for states. And in particular, in this case, the states of the system are labeled by a scaling dimension, a spin, and a momentum. Another implication of this extra symmetry is that the correlation functions are constrained by the symmetry. So an example correlation function might be the overlap between an excited state, delta JP, and then you make two measurements on the excited state, measurements at points x1 and x2, and then you ask what's the overlap of that with the vacuum. So this is an example of a transition amplitude you might want to compute in the theory. And the nice thing about all this symmetry is that it fixes this transition amplitude up to a single unknown coefficient here called lambda delta J. So lambda delta J is some kind of unknown thing, but the function of positions and momenta and delta and J is completely fixed by symmetry. You can think of it as being like a spherical harmonic. Okay, so conformal symmetry is a useful organizing principle for the theory. And now we're ready to understand where these three key constraints come in bootstrapping conformal field theories. So let me explain what these constraints are, and I'll explain it in the context of the simplest observable where they become really non-trivial, which is a 4-point correlation function. So we're going to be interested in a 4-point correlation function. So this is the expectation value of 4 measurements made at 4 different points. So the measurement here is called phi, and we're measuring it over here at x1, x2, x3, and x4, and we're asking for the vacuum expectation value of that measurement. So the first constraint is unitarity, and unitarity is basically a blanket word for the structure that we usually assume exists in quantum mechanics, namely a positive semi-definite or a positive definite inner product on the Hilbert space and Hamiltonian evolution that respects that inner product. And here unitarity is being used in 2 ways. One is to insert a complete set of states. So we take this correlation function, and here we're inserting a complete set of states between the pairs of operators. So let's see if this works. So here we're cutting a correlator between 5x1 and 5x2 and 5x3 and 5x4, and we're inserting a sum over all the states in the theory. So we have a sum over delta and J and an integral over momentum. And a second way in which unitarity is useful here is it lets us write this transition amplitude as the complex conjugate of another transition amplitude. Okay, so the next constraint is symmetry. And I already talked a little bit about the implications of conformal symmetry. They let us simplify certain kinds of transition amplitudes using the symmetry. And in this case, we can plug in the result from the previous slide, which was a result for the form of this transition amplitude that said that it's fixed up to an overall constant. And the result is a new expression for the correlation function as some kind of sum over quantum numbers. And this slide is very technical, and I don't need you to understand to remember all the technical details, but what I want you to take away is the template here of this expression. There's some unknown stuff, but it's positive. And then there's some known stuff that's fixed by symmetry. And positivity of this unknown stuff is coming, again, from unitarity. This is a general consequence of the structure of quantum mechanics, and it shows up over and over again in quantum mechanical observables. Quantum mechanical observables have some positivity properties, and that positivity is ultimately coming from positivity of probabilities, the existence of this positive definite inner product on the Hilbert space of the theory. So positivity is built into quantum mechanical observables, and that will be the key thing that, that we'll exploit. So there's something positive, and then there's something fixed by symmetry. And then the last constraint is causality. And the form of causality that we'll use here is that a commutator of 2 measurements at space-like separated points is 0. So if I make a measurement over here and a measurement over here, and if it's not possible to send a signal between the 2 space-time points, then the measurements have to commute with each other. The interesting thing is that this expression here that we got using unitarity so what causality means is that our correlation function should be invariant under swapping x2 and x3. But this expression we got from unitarity isn't obviously invariant under that. So we get an interesting constraint on the theory. And this is the first instance where we can see these conditions, unitarity and causality, cutting across each other in an interesting way. They're combining to be something more than just the individual constraints. So in the end, we end up with a consistency condition on our theory. And this consistency condition has this structure coming from quantum mechanics, a sum over quantum numbers of some positive stuff times some stuff that's fixed by symmetry. Okay, so this is an extremely complicated constraint. So how do we get interesting information out of it? So the problem is it has lots of moving parts. It has these quantum numbers that we don't know a priori, and it has these coefficients that we don't know a priori, but we do know that they're positive. And then it has all these different space-time points that it depends on. And there's a very general tool for getting information out of these kinds of constraints that we can use, which is the idea of using linear functionals to prove things about the theory. And this idea first appeared in the conformal bootstrap context in 2008, but it actually goes back even earlier to mathematical work on sphere packing by Kohn and Elkies, who used this strategy to bound packings of spheres in d-dimensional space. The strategy is to take your equation, your consistency condition, and use the fact that it has some positivity built into it, and apply different linear functionals to get different inequalities that prove different things. So as an example, suppose we can find a linear functional alpha that's positive, acting on all of the objects appearing in the equation. If we can, then we can apply alpha to this equation and get a contradiction. We end up with a sum of positive stuff times positive stuff is equal to 0. And that's, of course, impossible. So this gives us a tool for ruling out hypothetical theories. So for example, if someone comes to you and says, I have a hypothetical theory, and I think it has a scaling dimension delta equals 5 and another one delta equals 7, and that's it. Then all you need to do is go off and try to construct a functional that's positive for delta equals 5 and delta equals 7. And if you can, you've ruled out their hypothetical theory. Now, there's another way of phrasing this statement, which is that if you have some functional alpha, then it lets you deduce something about the spectrum. So for example, a consistent theory has to contain quantum numbers such that alpha is positive and quantum numbers that such that alpha is negative in order for this sum rule to balance out. This is the same as the previous statement, but it's maybe a slightly more useful formulation of it. So an example of where this is useful is, suppose you can construct a functional that's mostly positive. So here's an example functional. This is, I'm plotting the action of the functional on this function f delta j of x as a function of delta. And let's suppose that it's positive for most of the j's, and at j equals 0, it's mostly positive, but then it has a little negative region here. Then you learn that the theory has to contain a scaling dimension in that negative region. Otherwise, it's not possible to satisfy the sum rule at the top of the slide. So the game becomes finding functionals that prove interesting things about the theory. And by putting together many, many different functionals, you can try to corner the theory and learn a lot about it. And I should say, I'm happy to take questions during the talk. So please feel free to raise your hand or type questions into the chat window, and I'll answer them. Okay, let me give a toy example of this functional procedure just for concreteness. So let's think about a toy one-dimensional theory. So this theory is characterized by a list of scaling dimensions. And let's suppose we have a consistency condition in this theory, which says that a sum of positive stuff times a function that we know is 0. And the function that we know, the example I'll take is this one. Z to the delta minus 1 minus z to the delta. And let's suppose also that there is at least one positive scaling dimension in this theory. So I claim I can prove something interesting about the spectrum of the theory. So let's consider the following functional. It takes a function f of z to its derivative at 1/2. Then we can evaluate that on this function, and we get 2 times 2 to the 2 minus delta times delta. And this functional has a positive region. It's positive when delta is positive, and it's negative when delta is negative. And so we can deduce that there has to exist a negative delta in the theory in order for it to be consistent. So that's an example of this kind of logic. And again, the challenge is to find linear functionals that prove interesting things. And usually what that means is we want functionals that are almost everywhere positive and negative in only various tiny places. And if they're negative in tiny places, then we can learn that the theory has something in those tiny negative places. And this problem of finding interesting functionals is a convex optimization problem. It's a convex optimization problem because we're looking for functionals that satisfy positivity conditions in order to be interesting. And solving large systems of positivity conditions is called linear programming. In some cases, you can do this analytically. So for example, in this toy example, I wrote down a functional that we can analyze analytically. But in the case of strongly coupled theories that are relevant for condensed matter physics, like the O2 model, by far the most interesting functionals come from computer searches. So one of the things that has happened over the last decade really is we've developed tools for doing these computer searches more and more efficiently and finding more and more interesting functionals that prove interesting things about these theories. So I'll just jump to the results for this O2 model that is related to the superfluid transition. So these are constraints coming from applying this functional method to 4-point correlation functions in the O2 CFT. And the claim is that by putting together the right set of functionals, you can prove that the theory has scaling dimensions that live in this island. So this blue island comes from using these bootstrap methods, combining all these positivity conditions. And the island is so small that it gives a high precision determination of these scaling dimensions. So these are the scaling dimensions of the lowest few dimension operators in the O2 model. Interestingly, the result that we get agrees with Monte Carlo simulations. So the Monte Carlo result is this big green prism here. But both Monte Carlo and bootstrap results disagree with the lambda point experiment. So the lambda point experiment, the error bars are these two big brown planes down here. Now, a single theoretical technique disagreeing with experiment is interesting, but maybe not cause for concern, too much concern. But two completely different theoretical techniques that agree with each other and disagree with experiment really is a cause for concern. The Monte Carlo simulation and bootstrap calculations are completely different. They use completely different inputs and completely different methods, and yet we get this beautiful agreement between them, which is, I think, extremely strong evidence that that there indeed exists this conformal field theory, and that its scaling dimensions are highly constrained, and that this idea that conformal field theory describes second-order phase transitions is robust in this case. But there's something funny happening with the experiment, and I don't actually know what the problem is with the experiment. Unfortunately, we probably can't rerun it anytime soon, unless anyone is good friends with Elon Musk. So I hope that that this measurement will be done again sometime, perhaps on a quantum critical realization of the same conformal field theory.
Shri has a question, I think.
Yes, go ahead.
Do you think you can unmute yourself, Shri?
Yeah.
Let's see who you can.
Yeah,
Oh, yeah, he's
yeah.
unmuted.
Yeah, in the space
Great.
shuttle experiment,
Yes.
you said there's no gravity, which is true. But aren't the accelerations, if it is done on the shuttle or this ISS, I don't know where it was done, or is it a free flyer?
The idea is that the experiment was done on the space shuttle while it was in orbit. So.
Won't there be some? There are accelerations as people are, moving around and all that sort of stuff. So it's not.
Yes, there may be if someone bumps into the experiment or something like that. I think that the point is that if there are pressure gradients in the sample, they're greatly reduced compared to what they would be.
Sure, I agree, but I don't know. Again, it's a question of numbers here. Yeah, I'm not saying they're running around in the space shuttle, but they will. It is not as truly falling as if it was isolated. If it was an orbiting satellite, it appears to me.
Okay, interesting. I mean, this is a question for the experimentalists who did the experiment, whether they took that into account in their error bars. I think the simplest explanation of these results that I'm showing on the slide is that they somehow misestimated their error bars. So, but I don't know how. Okay, any other questions? Okay, so these techniques are pretty widely applicable to these kinds of phase transitions. And using similar techniques, we resolved an old problem about Heisenberg magnets. One of the things you can show is that Heisenberg magnets, which are isotropic magnets, are actually unstable on a cubic lattice. So this means that in practice, it's nearly impossible to realize them in the laboratory in a material with cubic lattice symmetry. You can also get high precision predictions for other phase transitions like the 3D icing CFT, which is relevant for uniaxial magnets and liquid vapor transitions. And we're currently exploring the simplest phase transitions and interacting phase transitions involving fermions in 3 dimensions using these techniques. And a lot of this is exploration. So it's kind of like being an experimentalist with a computer instead of with a laboratory. We don't really know the full extent of these constraints, and it's something that we're still exploring. There's been some interesting analytic progress in actually proving optimal bounds on certain very simple theories. One of these optimal bounds that made a splash recently was an optimal bound on sphere packing in 8 and 24 dimensions, which turns out to be equivalent to an optimal bound on certain kinds of one-dimensional conformal field theories. But it's not obvious whether one should expect analytic control of these complicated 3-dimensional phase transitions. And another interesting approach is trying to develop algorithmic techniques for getting more and more precise results. We're taking these islands and shrinking them smaller and smaller. This would be a kind of Newton's method for conformal field theories. So when I was in algebra class and I first learned that there's no quintic equation, I was pretty shocked. That I couldn't believe that something that simple didn't have an analytic solution. But in some sense, it's okay because we have Newton's method, so you can solve any quintic equation up the wazoo as well as you'd like. And what would be wonderful is if we had similar tools for these kinds of strongly coupled phase transitions. Okay, so that's the first physics problem, and hopefully it motivated for you the idea of using these consistency conditions and the fact that they can have surprising power, and also gave you a sense of the structure of the conditions, namely that there's some positivity that's coming from quantum mechanics, and this positivity interacts in an interesting way with causality and symmetry. Okay, now this next part is motivated by a conversation. Oh yes, that's it. I'll go back. Go ahead. You have a question?
I think you can mute yourself.
Could you please elaborate on the first point? Similar methods for your free model producibility.
Yeah. So Heisenberg magnets are magnets with O3 symmetry. So that's full rotational symmetry. So they're described by the O3 CFT, and there is if you're in a material that's on a cubic lattice, then there are microscopic sources of O3 symmetry breaking. That is just the structure of the lattice breaks the rotation group to the cubic group. And so the question is, does that breaking of the rotation group survive at long distances? If it's possible that it doesn't survive at long distances and that full rotational symmetry emerges, but it's also possible that the breaking of cubic symmetry grows at long distances and that begins to dominate. And this is a question that you can phrase in terms of conformal field theory. It's a question about the scaling dimension of a certain operator, an operator that it's a 4-index tensor operator under O3. And we proved that that 4-index tensor operator is a relevant operator. It's relevant, and so its effects grow at long distances, and it destabilizes the rotationally symmetric fixed point. Does that answer your question?
Yes. So this refers to spatial symmetries being discrete on the lattice, and the spatial rotations do not emerge in this case in
yeah, that's exactly right.
I see. Thank you.
Sure. Other questions? Okay. Okay, so this next part begins with a conversation. So at the beginning of the conversation, Albert Einstein tells us that general relativity has a beautiful formulation in terms of an action principle. And I thought this was just completely remarkable when I first saw this equation. You can summarize Einstein's equations in this really simple way. There's an action. The action is an integral over space-time of about the simplest thing you can write down, that the simplest non-trivial thing you can write down that depends on the geometry of space, which is the volume form times the curvature, the scalar curvature. After you get over how amazing this is, you might ask, well, wait a minute, why is the action so simple? Why can't we write down something more complicated, some more complicated function of the geometry? So for example, we could have r squared and r cubed terms and so on. So why is the action of general relativity simple? And I should say, on this slide, I'm ignoring the cosmological constant, and that will make an appearance later in the talk. Maybe the simplest answer, initial answer to this question is dimensional analysis. And this is the answer I got from my physics professor when I asked this question in my first GR class. We observed that the dimensions of the curvature, scalar curvature, are like mass squared. So that means that in order to write down this expression, these coefficients, alpha and beta, have to have the right dimensions. So we need a 1 over capital M squared and a 1 over capital M to the 4th in front of these terms. And it's natural, according to effective field theory lore, it's natural to say that this capital M should be the scale of new physics. That is some sort of scale that's above the scales that we're including in our effective field theory. And that scale is big, and therefore these terms are small. But this isn't really a great answer because, well, why can't there be large numerical coefficients in front of these terms? So sure, we have suppression by 1 over M squared and 1 over M to the 4th, but why can't we stick something big, some numerical factor in front of that? And there's a more refined answer to this question due to Kamanho, Edelstein, Maldacena, and Jubiadov from a few years ago, which is causality, one of those principles, bootstrap principles that I mentioned earlier. So the claim is that if these numerical coefficients are too big, then you can build a time machine. So what that means is you can construct a scattering process such that the signal comes out before it went in. Technically, the way this works is that in general relativity, when you scatter two things past each other, there's this famous Shapiro time delay. So you can get some intuition for the time delay by just imagining two things that go past each other, and suppose they got stuck in orbit around each other for a while and then they flew off. So that would be a really long time delay. You know, they could orbit around each other for 1,000 years and then fly away. Even if they don't orbit around each other, there's still some effect of the gravitational field from these two things moving past each other, and it causes them to come out later than they would have if they didn't interact gravitationally. That's the Shapiro time delay. The interesting thing that these people pointed out is that in the presence of higher derivative terms, so these higher powers of R in gravitational action, you can actually get time advances. And if you accumulate enough of these time advances, you can construct one of these time machines. The issue with this argument is that it's parametric. It tells you that you should be able to make a time machine if you make the coefficients of these terms arbitrarily big, but it doesn't tell you how big you have to make them before you really do have a time machine. So our graduate student asks, how big is too big? Okay, Stroll has a question in the chat. Isn't that action due to David Hilbert predating Einstein? So yeah, yes, I'm sure you're right. Okay. Thanks for pointing that out. All right. Any other questions or comments? Okay. So what we'd really like here are sharp bounds on these coefficients of higher derivative terms. And that would be the really ultimate answer to this, this inquisitive graduate student. Now, as is hopefully clear from the first part of the talk, sharp bounds can lead to predictions. So for example, suppose a few hundred years from now, LIGO discovers an R-cubed correction. Then if we have sharp bounds on these corrections, they can look up the bound and deduce the existence of a new massive particle. Now, if you ask someone working on LIGO, or if you ask a string theorist whether it's likely that they're going to discover an R-cubed correction, they'll say it's not likely. But even that not likely statement comes from an expectation about the size of these R-cubed corrections. And it would be nice to really know how unlikely it actually is. So we would really like to know how big these corrections can be. And when you have sharp bounds, that connects different areas of physics. So in particular, these sharp bounds can serve as a kind of low energy window into high energy physics. Beta is a quantity in the low energy Lagrangian. It's something that you could measure with a low energy experiment in principle. And capital M is a high energy quantity. It's something associated with the scale of these extra massive states. And we'd like a connection between them. And in general, a connection like this helps us understand what is possible in the theory of quantum gravity, which is also a worthy goal. Okay, so a different way of phrasing this, this goal is in terms of what's called the swampland. So the swampland is the space of low energy effective field theories that cannot be completed to a fully consistent theory of quantum gravity at all energy scales. Another way to phrase it is that the swampland is the complement of the landscape. So the landscape is the space of low energy effective field theories that do come from consistent theories of quantum gravity. So here's a picture. This is the space of all low energy effective field theories that you could write down. Basically, it's the space of Lagrangians that your professor could write on the blackboard for you. And when you write down Lagrangians, you can choose their coefficients willy-nilly. There are no obvious constraints. The claim is that most of those Lagrangians are secretly sick. They secretly cannot come from a consistent high energy theory. And those ones that are sick are in the swampland, where you have to look out for dragons. The ones that are not sick are in the landscape. So they come from a consistent theory of quantum gravity. Of course, the standard model should be in the landscape. And there are other theories in the landscape that we know about. For example, Tech 2b supergravity on ADS5 plus S5 is in the landscape. Okay, so there's this interesting structure on the space of effective field theories. And right now, it's mostly hidden from us. And we'd like to see this structure. We want to find the boundaries between the swampland and the landscape. That's just another way of phrasing this problem from the previous slide. Well, actually, I should say this is a more encompassing, all-encompassing way of phrasing the problem. Of course, there are other kinds of swampland constraints you might consider beyond just these constraints on higher derivative terms in the action. So this is sort of a more general program. But I'll be focusing on these constraints on higher derivative terms. Any questions or comments? Okay. So instead of talking about gravity, I'm actually going to talk about a more toy problem, which is a scalar field coupled to gravity. And that's because the formulas are simpler, and also because we haven't completely worked out the gravity case, my collaborators and I. Yeah. So we're going to be looking at a scalar field coupled to gravity. So it has this action. And the analogous question for this theory is, are there bounds on these higher derivative terms in the scalar field action? So G2 and G3 and so on. And I should say, I'm writing these actions schematically. So what you really have is 4 derivatives and 4 scalars, and their derivatives are contracted with each other in some way. And I'm just suppressing that for simplicity. These coefficients by dimensional analysis should be suppressed by some mass scale. And we would like a sharp bound relating that mass scale to the scale of new physics. And the key tool for deriving these sharp bounds are some rules called dispersion relations. So here I've sketched a little derivation of a dispersion relation. The idea is to look at the scattering amplitude and look at a scattering amplitude in the theory and use some kind of bound on the high energy behavior of the scattering amplitude. So here, these are plots in the S plane. S is the energy squared. If you know that the scattering amplitude is sufficiently bounded at high energies, you can write some kind of contour integral around infinity that's 0. And then bringing the contour inside, you get a relationship between high energy things and low energy things. So these cuts are contributions from high energy states. And then this contour integral around the red x's is something that you can compute at low energies. And again, you don't need to understand all the details here, but if you want to remember the derivation of a dispersion relation, you can just remember that it looks like a smiley face that's winking at you. So the end result is an equality between some low energy stuff and some high energy stuff. The low energy stuff is over here. These are coefficients in the low energy effective Lagrangian combined together in some way. And P here is a momentum. It's the transverse momentum of the scattering process. It's the amount of momentum that's its conjugate to the sort of impact parameter, the distance between the two things that are blasting past each other. So that's a parameter that you can choose. You can set up different scattering experiments with different transverse momenta, and you get a dispersion relation for each one. And the right-hand side has to do with heavy states. And I want you to notice that it has the same structure as the kinds of expressions we were writing before in the conformal bootstrap case. There's some kind of sum over quantum numbers, which we don't know. We don't know the masses of the heavy states of the theory. And there's some unknown coefficients, but they're positive. And this positivity is a consequence of unitarity. It's a consequence of this fundamental property of quantum mechanics that has that positivity is built into it because of positivity of probabilities. And then finally, there's some kind of function here that's fixed by symmetry. And this PJ is a Legendre polynomial for those of you who want to know all the details. So this expression has a kind of similar structure to what I was talking about before, and we can try to attack it with the same kinds of techniques. But first, I want to highlight some of the assumptions that go into this. So it relies on some assumptions that we like, namely unitarity. So that's responsible for this positive structure here. And Poincare symmetry, so rotation, Lorentz symmetry and translation symmetry. So those are nice, we're happy about those. But it also relies on some kind of boundedness assumption about the scattering amplitude, and also some kind of assumption about the analytic structure of the scattering amplitude. And those we may be less sure about. Okay, so it's important to highlight those. But let's forge ahead. And there's a classic result in non-gravitational quantum field theory using this dispersion relation due to Adams, Arcani, Hamed, Dubovsky, Nicholas, and Rattazzi from 2006. And the claim is that in a non-gravitational QFT, this G2 coefficient, so G2 is the coefficient of the 4 derivative term in the scalar field action. This G2 coefficient has to be positive. And the way you prove it is you take this equation at the top and you set P equal to 0. And remember, in a non-gravitational theory, this term isn't present. So this 8 pi G, G is Newton's constant. So if there's no gravity, this term isn't there. So we can set P equal to 0. And we get that 2G2 is equal to a sum of positive stuff times positive stuff, which is bigger than 0. this is an instance of this linear functional technique. It's a really simple instance. The linear functional is the thing that just evaluates something at p equals 0. So we chose a functional and it taught us something interesting, that this G2 is positive. And this result is actually related to causality. So there's a separate argument given in this same work that shows that if G2 were negative, you could build a time machine, similar to the time machine of Kamanho, Edelstein, Maldacena, and Ibayadov. It shows this dispersion relation is a sort of more precise way of recovering these time machine arguments in this context. But if we're in a theory of gravity, things are trickier. So one is that we had these assumptions. We had to assume something about the behavior of the scattering amplitude at high energies. And another is we had to assume something about the analytic structure of the amplitude. And then there's a more annoying technical problem, which is that we just can't set p equals 0 in the case of gravity, because there's this pole that is coming from graviton exchange. So this is basically the propagator of the graviton. And it becomes infinity if we set p equals 0. Okay, so this first problem, behavior of the scattering amplitude at high energies. The real problem is that we don't have a fully rigorous, non-perturbative definition of quantum gravity in flat space. If we did, we might be able to attack this problem of how does the scattering amplitude behave at high energies. Now, people can make guesses about the high energy behavior and well-motivated guesses, and there are lots of proposals out there. But if we really wanted to be sure, we would need some actual definition of quantum gravity. So we should go to a case where we do have an actual definition of quantum gravity, which is ADS-CFT. So ADS-CFT, you've probably heard of it. It's a definition, a rigorous, non-perturbative definition of quantum gravity in the case of a negative cosmological constant. The statement of ADS-CFT is that quantum gravity in ADS d+1, the simplest negatively curved space, is equivalent to a conformal field theory in d dimensions. And the picture you can have of ADS-CFT is this sort of soup can picture. We have a conformal field theory that lives on the outside of the soup can, and the theory of quantum gravity is the soup on the inside. And the claim is that observables in conformal field theory can be computed from gravity and vice versa. So, for example, 4-point correlation function, like the thing we were talking about before, so it would be associated with 4 points on the boundary of this picture, becomes related to some kind of scattering process inside ADS in a theory of quantum gravity. And the nice thing about this is that the axioms of conformal field theory are rigorous and well understood. And this allows us to use these conformal bootstrap techniques to constrain theories of quantum gravity in ADS. So all these functionals that I was talking about before that constrain the O2 model, the O3 model, the 3D Ising model, and so on, we could apply them and learn something about quantum gravity in ADS. Now, it turns out that to really learn interesting things about quantum gravity in ADS, you need to construct very special kinds of functionals. And this is something that the Bootstrap community has learned how to do over the last couple of years. It's been understood recently how to construct functionals that behave like dispersion relations in ADS. And in fact, in upcoming work that will hopefully appear next week, my collaborators and I write down a precise dictionary between CFT functionals and flat space dispersion relations. So precisely what functionals you need to apply to CFT correlators to give you dispersion relations in ADS that look just like the ones we've been talking about in flat space. So this is a rigorous approach to dispersion relations, but in a different kind of space-time. The nice thing about it is it solves all of the problems from before. So one is that the high energy behavior of the amplitude in this case is actually controlled by a theorem in conformal field theory, which is the so-called bound on chaos by Maldacena, Schenker, and Stanford. The analyticity properties of the scattering amplitude are also controlled by the structure of the conformal field theory. And also there's a natural strategy for dealing with this graviton pole problem that actually works in both flat space and ADS. So if you take the limit as the cosmological constant goes to 0 of these CFT constructions, then it gives then the interesting thing is that we land on exactly the flat space dispersion relations I was writing before. So this gives confidence that the flat space dispersion relations are at least reasonable. To prove that the flat space dispersion relations are absolutely correct, we would need a holographic formulation of quantum gravity in flat space, which we don't have. But at least this is motivation for considering them. But also we get something practical, which is we can use a strategy, a bootstrap strategy, to get information out of these flat space dispersion relations and learn something about flat space physics. So let me talk about that strategy. This is the strategy for dealing with the graviton pole. There are 2 steps. Remember, the problem with the graviton pole is that we had some kind of sum rule, and gravity meant that we couldn't set p equal to 0 in the sum rule. And that meant that we couldn't reproduce this argument of atoms at all, showing positivity of G2. And the idea is to not try to set p equal to 0, but instead try to control large p. So a large transverse momentum. And that's equivalent to studying scattering at small impact parameters. So scattering of 2 things that are blasting past each other really, really close by. And the idea is to derive dispersion relations that hold up to those larger momenta. And then that gives you a sum rule that looks like this. And now you can look for other kinds of functionals acting on this sum rule. And the key functionals turned out to be ones that really exploit this large momentum behavior by integrating up to large momentum. So you look for some function f of p such that when you integrate it against the right-hand side, you get something positive. So this is this bootstrap technique. You look for positive things. And then if you can find this f of p, then integrate it against the other side of the equation, you get an inequality. This problem, finding a function of momentum such that this is positive, is a convex optimization problem, and we can use the same techniques to solve this problem as we use in the conformal bootstrap. And in fact, the same numerical tools, the same semi-definite program solver. This gives a set of convex optimization problems that you can solve and get bounds on gravitational EFTs. And these are the bounds we get. These are bounds on the coefficient G2. So maybe this is a little small to read, but this is G2 times m squared, where m squared is the mass of the lightest the lightest massive particle that's not included in the gravitational EFT. So G2 m squared over 8 pi g, and this is G3 up here. And the claim is that these coupling constants are constrained to lie to the right of each of these curves. So here's the curve for d equals 5 dimensions. So the coupling constants have to live out here to the right of that curve. So this region is allowed, and this region out here is disallowed. And one of the interesting things is that with gravity, G2 can be a little bit negative. So you might remember this result that G2 is positive in QFT can be related to a kind of time machine experiment. The claim is that if G2 is negative, then it can lead to a time advance, and you could use that to build a time machine. But the sort of intuition for this result is that gravity has a kind of inbuilt time delay, the Shapiro time delay, and that together the time advance from G2 is canceled by the time delay from gravity. It's difficult to take that intuition and turn it into a precise thought experiment. That's the problem with these time machine experiments. They just give sort of parametric results. They don't give precise results. The precise result is this plot. Now, everyone here who lives in 4 dimensions must have noticed that there's no d equals 4 case on the plot, which is the case of interest for us. There's an interesting new technical issue that appears in d equals 4, which is the appearance of an infrared divergence, a long distance divergence in the bound on these quantities G2 and G3. This divergence is actually fixed. It is actually fixed in ADS. So this is another nice thing about studying ADS CFT. We can learn mechanisms for fixing these problems, but we don't know yet how to import that mechanism into flat space. So that's an interesting open question. There's a question from Misha in the chat. What if you add higher operators, G4, G5, and so on? That's a great question. So this, you can indeed put bounds on G4 and G5 and so on. And there are two-sided bounds on all of those coefficients. In G4 and G5 don't affect the bounds on G2 and G3 that I'm showing here. And the reason is that only G2 and G3 appear in this dispersion relation. One of the key things is to write down a dispersion relation such that the left-hand side is exact. This is different from usual dispersion relations. Usual dispersion relations have an infinite series of corrections on the left-hand side. This one, this improved dispersion relation is exact. It has only these coupling constants that I'm showing here. And that's the thing that really lets you get control. Now, I have to say that this exactness is only true at tree level. If you include loop corrections, then there would be loop corrections to the left-hand side, and those would turn into loop corrections, computable loop corrections to the bounds. Does that answer your question, Nisha? Okay, I'll assume it's okay. Please ask more if you want. Okay. So I'm wrapping up. So these techniques for putting bounds on low energy EFTs using bootstrap methods, I think are very widely applicable. And an interesting thing is to apply them to general relativity and Einstein-Maxwell theory and other interesting EFTs. And this is work in progress. An important conceptual question is to resolve this IR divergence problem in 4 dimensions. I should say that the way it's resolved in ADS basically introduces an extra logarithm of m, a logarithm of the heavy mass into the bounds. So it actually doesn't change the bounds that much. And I expect that that the same will be true. I think the same will be true in flat space when we figure out the mechanism for solving the problem. I don't think it's a fundamental problem. And the part of the reason is that all of these constraints are really coming from short distance physics, and the IR issues only enter in one hopefully controllable place. But anyway, that's a very important thing to get a handle on. Another interesting question is whether we can write down dispersive sum rules for positive cosmological constants. So that's obviously also important for our world. And that's an open question that lots of groups are thinking about. I think it's a really interesting one. Another question is whether there are any differences between these different cases. So interestingly, the bounds that we get in ADS are the same as the bounds that we get in flat space. So that's maybe a little bit surprising. And so perhaps with even more sophisticated functionals, we could end up proving things about flat space that are different from ADS or vice versa. Another interesting question is to explore the theories that saturate the bounds. So I didn't get to talk about this, but in the conformal bootstrap, there's a plot of bounds on scaling dimensions in the 3D Ising model, and the 3D Ising model lives at a sort of corner of this plot. And so you could stare at this plot here of bounds on gravitational effective field theories and ask, well, what lives there? And I don't know. And it's interesting to ask whether there's a theory that lives there. And generally in the bootstrap, by exploring the sort of corners of these bounds, you can sometimes find theories. So there's a question of whether we could maybe rediscover string theory, which is an example of theories of quantum gravity that obey these bounds. Or maybe find a new kind of theory of quantum gravity. And the dream for this program would be a complete map of the swampland and the landscape that is optimal bounds and a classification of theories that saturate them. I'll stop there. Thanks a lot.
Thank you. So I think we have time for questions or comment. I think you can raise hands if you have any questions. Yeah, I think Alexi has a question, so you can unmute yourself.
Can such techniques be applied to non-relativistic settings? For example, with dynamical exponent not equal to 1, or even more extreme settings where low energy fields reside not at points, but say on lines. So such systems are of interest in condensed matter physics context.
Yeah, that's a great question. So the sort of theme that's emerging is that we don't really yet know how much symmetry is enough to really make powerful progress with these techniques. Conformal symmetry seems to be enough to get some really precise results. In the case of these gravitational effective field theories, Poincare symmetry is enough. And so I don't know the answer to your question. At some point, as you reduce the size of the symmetry group, it gets harder and harder to get precise results. The bounds get less and less constraining. There has been some work on studying non-relativistic conformal field theories. That a bootstrap program for those has yet to get off the ground because the sort of axiomatic status of those theories is a bit different from regular conformal field theories. In particular, the problem is that there's no obvious state operator correspondence, which is a sort of important thing for the, it was implicit in what I was doing that I didn't talk about. But so there hasn't been much progress on that yet. Regarding your other question about theories where excitations live on lines and so on, I'm not sure I know precisely what kinds of theories you have in mind, but certainly these bootstrap techniques are useful and have been used for topological field theories, where you know they're characterized by some spectrum of anyons and grading statistics, and there's some kind of modular tensor category underlying it. These modular tensor categories can be explored using bootstrap techniques as well.
Okay. Shuri has a question. Shuri?
Yeah, this is a crazy idea. Feel free to immediately dismiss it. But decades ago, there was this proposal by Dirac, which of the large number hypothesis. And essentially what it does is it relates things that happen on the larger scale, which is the universe, to things that happen on the smaller scale, which is sort of, you know, physics or physical constants. And the idea is there's some, I don't know, I don't remember exactly, but it started off with a sort of a similar spirit. You take a bunch of constants. Now it would include G and E and M and all that. And then you take another bunch and then they have dimensionless and you say, okay, and they have to be large and you equate them. And then you find one of them, like Hubble's constant, because it's there, is going to change with time. And so, you know, that therefore the whole thing evolves. I don't mean to equate that whole thing to what you're saying, but it's an, you know, I just want to bring to your attention, there's this sort of a dimensional approach, which was popular 40, 50 years ago. And I don't know if, I don't think anyone took it seriously, but since it was Dirac, you know, everyone quotes it. It was someone like me who proposed it, it died immediately in a microsecond. Anyway, I just thought I'd bring it up with no particular vision of how you'd go and take advantage of that sort of a approach.
Okay, well, thanks for the comment. I guess I have some reading to do.
Okay, any other questions, comments, suggestions for future research? So when you say that there is no difference in consequence of dispersion conditions on ADS and flat space. So for example, in your graph of G2 and G3, there are no lambda dependence. Is that?
Yeah, that's right. So I mean, I should say that in this plot, the idea is you construct a positive functional. And if you construct a positive functional, you get a bound. And so for the positive functionals that we've been able to construct, give the same bound in ADS and in flat space. By the same bound, I mean bounds that are the same in the limit that our ADS is large. So the bounds do get 1 over RADS corrections.
Oh, okay.
Computable 1 over RADS corrections. But the question is, in the limit where 1 over RADS is large, the bounds are the same. And that's what you might naively expect. And the physics of it is just that these bounds are kind of coming from short distances and they don't really care about the global structure of the spacetime.
Oh, I see. So that when you say that there is no difference, meaning that no difference between ADS in the limit of large ADS curvature versus direct calculation in flat space.
Exactly.
Oh, okay, great. Thank you. So that sort of gives confidence about this type of reasoning. It seems.
Yeah, that's right. And it's non-trivial that that's the case, because if you take a flat space functional and you apply it in ADS using the dictionary that we worked out, you still get something you need to check. So basically, there's a regime in ADS of very large impact parameters that are much bigger than the scale of our ADS. And it's not guaranteed that your functional is positive in that regime, and you have to check it. And so far, for every case that we've checked, it is positive. So that's what I mean by the bounds being the same. And so far, it's been the same in all the examples that we know of. But it's possible that with more sophisticated functionals, you could generate an example where they're different.
Good. Any other questions? I don't see any hands, so I think people are all satisfied. So let's thank David again.
Thanks a lot.